Okay, so if you take a look at this, so once again, let me review that point that I tried to make, even though it's not, I'm certainly not an expert or qualified to talk about it more than like 30 seconds in a row, is data and how you discover pattern in data through linear algebra. So you stretch the data that is kind of random around, randomly thrown around the origin. You stretch it in such a way that it becomes thin in one direction and then elongated in another direction that suggests that there is a pattern of dependence between the two variables. Okay, so if we go back to linear algebra, then and the pictures that we have seen, you take a circle and then a linear operator will stretch it. We could stretch it along the axis, or more typically not along the axis, and then once again to discover in which direction it's happening and what that stretch is, the key idea to separate the two directions and find the relation is then we can do it with linear algebra, and in fact to find that particular direction is to solve that equation at the very bottom. Okay, so that is the key equation to the whole thing. So once again, this is the picture. Transform the plane into the plane. It is certainly as a linear operator. So, and then we ask ourselves, is there such a vector along which there is nothing that the operator is doing other than stretching? So in this particular stretching is lambda. Okay, so lambda is the factor or coefficient. What is the word I'm looking for? The degree of stretch. Okay, so you can see that roughly, in fact, and then there will be two. We would expect to have two. Because, well, there will be possibly another one, maybe a perpendicular, maybe not, say u, and as you can see, it will be also stretching, but at a different degree, and then so there will be two different factors like that for two different directions. In between, as we know, there will be rotation. So if we have examples that we have seen, and we can do it again, is two disproportional stretches in two different directions will also create a rotation between them. So let's do that example. I think we should do that example. So a typical example is given by this very simple diagonal matrix. So diagonal makes everything very simple. Okay, so in this particular case, we already know that it will be stretch by 2 horizontally and stretch by 3 vertically. So we know that, and how do we know that? We can to explain why this is the case, just in case, we could how do we prove that it is stretched 2 horizontally and 3 vertically? How to explain these words algebraically before we go on with our equation over there. Stretched by 2 horizontally and by 3 vertically.
2x plus 3y?
That yes, but still, I'm trying to say here that there are 2 consecutive. That's the hint for you. There are 2 consecutive steps. Stretch by 2 horizontally, in the second step, stretch by 3 vertically.
So is that like the identity matrix multiplied, like matrix is just 2 and 3?
Yeah, that's right. So twice, two steps, will be it's a composition. That's what consecutive means. So you'll have 2, 0, 0. Well, depending on the way I'm writing here, it will be in the opposite order. So it will be 1, 3. And 2, 0, 0, 1. Okay, so I have separated the 2 steps into 2 steps described on the left, on the right, into 2 matrices applied consecutively.
What's the word beside, like
stretch by 2 horizontally by 3 vertically.
Matrix 2, 3.
diagonal?
Yeah,
Yes?
yeah.
Diagonal, yeah. So when the diagonal matrix, it's easy to break it into two consecutive diagonal matrices applied, and you know what multiplication of matrices stands for. It stands for composition of those operators. So if you look at the first operator, it keeps the horizontal direction intact and the vertical direction is stretched by 3. The second one, or rather the first one, is the second matrix, but in the applying in the opposite order, it keeps the vertical intact and it stretches horizontally by 3. So you can do it consecutively, and these are matrices are simpler than the original one. It's kind of a decomposition into steps, that each of which can be described in these simple terms. Okay, so that's just an explanation. We're really trying to come up with an idea of how to solve this problem over here in a manner that does not require any kind of insight or into the geometry. In fact, it is the solving this equation will tell us what the function does. Okay, so we're starting with an obvious example, a diagonal matrix, and so we know what it's doing, and that's why when we discover, we analyze the equation, we'll just confirm it. Okay, and then hopefully we'll consider more complex cases. So okay, so my matrix is 2, 0, 3. So and then find V such that FV is equal to 2V stretched by 2, and FV, well, let's name them, V1 and V2 is equal to 3V2, like this. So we have two separate stretches. We know the factors are 2 and 3, so let's find the vectors. From the picture, if you it should be very predictable, right? So the description here is self-explanatory. Stretched by 2 horizontally. What is the vector? What is that vector? Stretch horizontally by a factor of 2. Give me an example of a vector that doubles. That's what we're saying here. F of V1 is F applied to V1. Okay, so it happens to be twice V1. So what can you give me one vector that doubles?
1, 2, 6, 2, 4.
No, 1, 2 is not going to work. No. 1, 2. Let's try. If I go with 1, 2. 2, 0, 0, 3. Remember what I forgot about. They make that point that I promised. What's happening between the two basis vectors? And they're actually, let's see, they actually get, that looks pretty bad here. 1, 2. Let's multiply, so it will be 2 and 2 and 6, right? So as you can see, the first coordinates doubled, the second tripled. However, it doesn't mean that the vector has either doubled or tripled or anything. In fact, 1, 2, which is this, has become 2, 6. 2, 6, like this. So there is a rotation there. I'm not doing that good job here with the. I do want to demonstrate the rotation clearly. So the first one is 1, 2, which is this, and the second one is 2, 6. 2, 6. Like this. They are not proportional to each other. Okay, so once again, this is V, and this is, or let's call it U, so there would be no confusion, and this is F U. Okay, so once again, think about it. How do you stretch horizontally? Stretching horizontally means simply that the x-axis is stretched. That's for sure, which means that the x-axis is not going anywhere. Okay, and then the y-axis is also stretched, which also it means it's not going anywhere. But it is done in a disproportional way, which means that the vectors in between diagonal vectors will rotate inevitably, because they will be stretched slightly more vertically than horizontally, and that gives you a rotation right there. Okay, so that's the difficulty. So just description that we have over there is really not that it is incomplete. It does hide this issue of what's happening in the direction that are not horizontal nor vertical, and we certainly need to address it before we deal with more complex functions. So this one is fairly simple. It is a stretch. It is diagonal matrix. So then we make that geometric description on the right more specific and algebraic, and we are sort of discovering it from the matrix itself. And so what I'm trying to do is to once again see the vectors that have been stretched purely. So stretch means, well, what does it mean to stretch a vector? You multiply, period. So that's constant multiplication of vectors is stretching of the vectors. However, with when you speak of the whole plane of vectors, you can the only way to stretch it is to multiply every single vector by the same exact number. That will be a stretch, and every vector straight goes like this, just becomes longer, same direction. But it is disproportional, so I have to do it one at a time, and I find, for example, the easiest one is simply 1, 0. Okay, and for the other one it is 0, 1. So the two simplest one that are stretched 2 and 3 respectively are the unit vectors, but also all of their multiples. So meaning the same what we just discussed. Along the x-axis there is every vector in the x-axis will be stretched by 2, and every one in the vertical will be stretched by 3. So, like I said, there is a stretching within the axes, but otherwise they're intact. They're not going anywhere, and that's why it becomes an issue with what's happening in between. So these are that's how we discovered those two vectors. And you can certainly guess that if I replace 2 and 3 with any other two numbers, we would be in exact same position. So diagonal matrix with two entries, positive or negative. They could be negative as well. The story will become exactly the same. Along the axes, there will be stretching, and elsewhere there will be both stretching of some factor and rotation. So what is the you don't even want to talk about stretching anymore, because if there is a rotation, then it's really not an issue anymore. You have a complex transformation. In fact, it is they not only they're rotating, but they're rotating also disproportionately if you think about it. So two vectors are fixed, and the vectors between rotate, but they rotate in a different rate. So they kind of fan like a fan. They spread out possibly, or some of them spread out, some of them are become closer. So it is a kind of a complex behavior, and to make sure that we have that, I do have a picture of that, of a little simulation. So this one, okay. So this one reverses orientation, so that is inconvenience. Let me do 2 and 3 here. Okay, so that's exactly what we just talked about. As you can see, the blue x-axis remains intact. The vertical brown remains intact, and then there are these 4 in between. The purple, as you can see, the purple has rotated counterclockwise, and the green one, but the green one rotated clockwise, right? You see it? The green one, no, it's also counterclockwise. Which one? Yeah. No, they all rotate in the same direction, but in different degrees, right? So because think about it, because the stretch along the y-axis is bigger, you kind of all the vectors are kind of pushed in that direction. You see it, right? So all of these vectors are closer to have become closer to the y-axis, right? Okay, so that's what we're talking about, and so you can have all illustrations of this kind, but but we have to really examine it algebraically. So what if the matrix is not diagonal? What is going to happen? Then the exact same thing can happen, but it might not be as obvious anymore. So the choice of those vectors that remain intact will be less obvious. So this is the place we are, and the answer was obvious from the beginning. So stretch horizontally, vertical, and so we knew that the vectors that are really stretched are only vertical and horizontal. The rest of them are not on the list. Another example, I think we keep running into that issue. So if we take 2 and 2, right? So that's a different situation, because fv is equal to 2v is in fact what's happening. V is any. So any vector will satisfy this equation. If the two factors of stretching are the same, it means that the stretching is the same, because f of v is equal to 2v. So it's true for every v. Okay, every vector is stretched, because this is the matrix of scalar multiplication by 2. Okay, so then we don't have, there is really nothing interesting happening, no rotation or nothing like that. So any multiple of the identity matrix will have this very simple behavior, but we are going into, once we change the factors, make the factors different, then there will be this complexity of things. So like this, not only stretching, but also rotations called by stretching, if you think about it, because once again the rotation in the y direction, as you can see, is higher than in the x direction. That's why the angle is not the same. It is closer to the y-axis. So even though on the surface, as we have described the function, we have nothing but stretch. That's what I put over here. But turns out that it is the stretching that causes other things to happen, and that's the rotation. Okay, but the starting point is still in this box over there. We have a stretching behaviors of in some directions, and that's the analysis really on a different level. Analysis of linear operators is to find out in what directions the operator stretches and nothing else. Once you found that, then the rest will fall into your lap. That's the idea, pretty much. So let's have some definitions. So we have a linear operator. Let's just stick with let's go n-dimensional. So it is a linear operator on same dimensional space. Okay, and then so suppose a v is equal to lambda v for some number lambda and non-zero vector v. Then lambda is called an eigenvalue. Of A, and V is called an eigenvector of A corresponding to lambda. Okay, so eigen stands for, it's German for characteristic. So in some literature you can find the word characteristic instead of eigen, and it's fine to use as well. So usually nobody gets confused about that. So that's the equation as I explained. This seemingly simple equation says it does exactly what we just discussed. It means that the vector v under A is stretched by a factor of lambda. That's what the equation is, right? So the left-hand side is simply we're asking ourselves what happens to V under A. A is the transformation of the space, and we answer. Sometimes we answer that it is simply a multiple. Okay, so we know that some of them will be satisfying, possibly satisfy this equation. Some will not. So not every vector is an eigenvector. We just saw it in the last example. That once vector is rotated by A, it's not an eigenvector anymore. Okay. But how do we find lambdas? Well, let's take it. It's really not that complicated how to find those eigenvalues. And in the example that we just saw, we are just go with this 2, 3. How do we discover 2 and 3? So xy is equal to, that's my vector V, this is my matrix A, and it is equal to lambda, which is unknown, xy. So we need to solve for x, y, and lambda, pretty much. Okay, so my matrix times V, and we need to find out whether or not this is satisfied. It's really not complicated because the matrix is diagonal. So I have 2x is equal to lambda x, and 3y is equal to lambda y. Okay, so in that case, so I end up with a system of linear equations. Okay, so a simple one at that. So here I have to be somewhat careful, and so as you can see, I have only x present, and so I have to consider separate cases. X not equal to 0. I'm looking at the first equation. I want to cancel x, but I'm only allowed to do that when x is not equal to 0. So if it's not equal to 0, I cancel x, and I conclude that lambda is equal to 2. On the other hand, if I'm looking at the second equation, let's do case 1 and 1 at a time. So case 1, x not equal to 0. I cancel x in the first equation. Then what happens to the second equation? Lambda is equal to 2. What happens to the second equation? If lambda is equal to 2 in the second equation, what do we conclude? There is one. There is one. 0. Right, so, well, okay, so that is informative because if we are looking for the eigenvector, we need both x and y. Turns out that x is not equal to 0, but y is, and that what is it? It's the any horizontal vector is it. Okay, case 2, I assume that y is not equal to 0 because I want to divide the second equation by y. I conclude that lambda is equal to 3 from the second equation, and once again I go to the first equation to find out what happens if lambda is equal to 3, and I discover the same way exactly again that x has to be equal to 0. Okay, so that way we simultaneously have solved both of the problems. One, find eigenvalues, and second, find the eigenvectors. So, well, let's list it. So there are only 2 possibilities for the eigenvalues, 2 and 3, and the eigenvectors are also have been described here. So, eigenvalue lambda is equal to 2. Eigenvectors are what? X0, x not equal to 0. X not equal to 0 is really an exclusion that is not substantial because we only exclude it because we do not want to throw the 0 vector into this mix. Because why not? Because it will satisfy the equation always. Whatever lambda you pick, the 0 vector will fit in. So it's just not interesting. And we want to separate eigenvalues from eigenvectors from different eigenvalues, right? Like from different fathers or different mothers, you know. So eigenvalue is equal to 3. Eigenvectors are 0, y. Once again, you assume if you have to that y is not equal to 0. And then there's a further language for this. We describe then here the x-axis. is combined, so this is the case for eigenvalues for lambda equal to 3, is the eigenspace of lambda equal to 2, and the y-axis is the eigenspace of the other one. So in other words, you take all the eigenvectors and add 0. And you end up with an eigenspace. For a good reason it's called a space, because it's line. So it is a subspace. Remember that discussion. So eigenspaces for each eigenvalue will be subspaces. So they could be a line or a whole plane. Okay, so that's at least in the two-dimensional case. So we already had two simple, the examples that we considered was the identity matrix, is everything is simple, and then the diagonal matrix, as you can see, you end up with a system of linear equations that is easy to solve, and you sort out things fairly simply, and you find the eigenvalues, eigenvectors, and then eigenspaces. Okay. And once again, so there are two lines. You only concentrate on them if you only care about stretching behavior, vertical stretching, horizontal stretching within those lines, confined to those lines. F will do stretching. Elsewhere, it does not. There is more happening. There is a rotation. Let's consider a different example. That you saw not a long time ago. It is a projection. So it's going to still be diagonal. So the projection on the y-axis. Yes. What's the matrix? Once again, don't try to think about the whole thing at once. All you have to do is to look at where the unit vectors go. So, and if you find those two vectors, those will be the two columns of your matrix.
0, 0, 1, 1.
You have to have the right order. 0, 1, 0, where does it go? Hold on, do I want on the x-axis or y-axis? Let's do on the x-axis, I think. Yeah, on the x-axis, it's just more comfortable. So 1, 0 goes to 1, 0, and the 0, 1 goes to what? Projection on the x-axis. 0, 1. What is it?
1, 0.
No. 0, 0. So the matrix is 1, 0, 0, 0. Okay, so let's work it out. Once again, all the eigen stuff. So I have my matrix, once again, 1, 0, 0, 0, multiplied by xy is equal to lambda xy. And once again, I need to find xy's and lambdas, and for each lambda I have to find, well, I have to find lambdas first, and then for each lambda I have to find all possible xy's. Okay? Eigenvectors. So the equations are simple, really simple. X is equal to lambda x. First equation, just like before. But the second equation is very simple because you end up with 0. So 0 is equal to lambda y. That is my system of linear equations. Okay? So once again, we are in the same place as before with the first equation. What does the first equation tell me? That analysis is at the very top is pretty much the same. So x not equal to 0. If x is not equal to 0, then we proceed to say that lambda is equal to what? 1. Okay, and then that doesn't answer the question about yet about as easily as last time about what are the possible values for y, because if I try to plug in y, well, no, I could if I plug in lambda equal to 1 to the second equation, what do I get? It's the same. Y is equal to still y equal to 0. Right? So that way we already have found one eigenvalue, and as well as we found its eigenspace. So the answer is exactly the same as the last time. Okay? Now the second one, what do we do with the second one? Well, let me write the answer for the first one first. So like this. Eigenvalue, lambda is equal to 1, eigenspace, what is made of eigenvectors is still the x-axis. Okay, now, okay, let me make this clearer. Okay, so that's the first equation. What about the second equation? I need to so both of the equations have to be satisfied. But this time I want to start with what? I would like to start with the second equation. What is 0? Lambda, okay. Okay, so lambda is equal to 0. That will satisfy our requirement. Lambda equal to 0. And if lambda is equal to 0, what we can say about y? Y is any. Okay. However, what does it tell us about x if lambda is equal to 0? What? X is 0, right. X is 0. Okay, so that gives me the second eigenspace. So eigenvalue lambda equal to 0. That indicates that there is a projection, eigenvalue equal to 0. It's like it's a collapse, right? So either we have a factor of stretching, shrinking factor, lambda equal to 1, 2, 3, or if it is 0, it is a collapse. So eigenspace. However, the eigenspace is the same. It is still the y-axis, right? Look at the second line over here. X is equal to 0, but y is any, so it is the y-axis. Okay, so once again, this is intact, and this one is a collapse. Well, it is a projection, but if you look at the concentrate on the eigenspace itself, then that's the idea of the analysis, to concentrate one eigenspace at a time and see what's happening there. So if we look at the eigenspace of lambda equal to 1, the x-axis, what's happening there? Nothing, because lambda x is equal to goes where does it go? It goes to x. Okay. If we look at the other eigenspace, the y-axis, what's happened to that? The whole thing goes to 0. That's a collapse. What? To the origin. What?
Shouldn't it be the origin? Like the eigenspace is the origin?
No, the origin is also the origin always goes to origin. Okay, so there is really nothing interesting to say about that. And we are certainly, if look at it, it works out. It works out. If you take any vertical vector is taken, it goes to 0, right? Every vertical vector, not 0 necessarily. Okay, so which means that, what does it mean? It means that every vector is multiplied by 0. Every vertical vector is multiplied by 0. That's the definition of eigenvector and eigenvalue. It just happens to be 0, and that's good news because we have covered the two eigenspaces, and that's the key to this analysis. Both of them are together. They span the space. It would be bad if we did not have the complete set of basis vectors acquired from this analysis. So the idea of eigenspaces and all this analysis is to have a basis made of eigenvectors. Okay, so right now it just happened to be our eigenvectors were all standard vectors, the unit vectors. But in general, once you have a stretching in some weird direction, that vector will be, in fact, our interest. And that is, so that picture that we looked at, this one, it is exactly what this is. This is what we're aiming at. Stretching in the direction other than the axis. Okay, and so then we want to know whether or not, so hypothetically it is possible, and we've seen examples of that. Then one, you can still have a total collapse from one of the directions. So that way your data does not turn into like a cloud, like stretched out ellipse, but rather just a whole line becomes a whole line. So that's the ideal situation. But in general, we expect to build a basis of eigenvectors. Okay, so let's do some more analysis that is, well, let me do some on a random example to appreciate the theory that we have developed. So A is equal to 1, 2, 3, 4. What is it? I don't know. But what I'm supposed to do now, I'm supposed to do as before. I'm supposed to solve this system. xy is equal to lambda xy. Okay, so I mean, it's not really that complicated, but there's a lot of work to do, because I have now x plus 2y is equal to lambda x, and 3x plus 4y is equal to lambda y. Okay, as you can see, this is more complicated, and the analysis that we have just done in the previous two examples is not going to work out anymore. So we would have to do more work. And to suggest in which direction we're going to proceed, it's better to have the whole thing written in vector notation anyway. To see what I'm talking about here, what if we move the whole thing to the left-hand side, the right-hand side to the left? So I'm going to have y and collect similar terms. I'll have 1 minus lambda x plus 2y is equal to 0. There are no free terms. That's the good news. So it is a homogeneous system. I will have zeros on the right. So that's the good news. 3x plus 4 minus lambda y. So that's what my new system looks like. Okay, but otherwise it is a system that we're familiar with. It is a 2x2 system. We certainly can solve it. We know how to solve it, and we might have to solve it. But there's a shortcut here for finding lambdas. Why? Because there was a theorem. There was a theorem that is, well, I'm not sure if you remember, but what we're looking for here is find xy not equal to 0. So suppose we're looking for lambda, but we don't know what it is. So we're supposed to find xy that satisfies the equation or equations. Okay, so do you remember a theorem about that? Solve a system of linear equations, homogeneous, and we are looking for a non-zero solution.
The one that says there has to be a solution?
It has to be what?
Like there's one that says there's always at least one solution, 0.
That's right. That is the theorem I'm referring to. So you remember what the requirement is. What guarantees? What fact about the system would guarantee the existence of such a solution? Non-zero solution, homogeneous system.
It's inverse?
It's the opposite. It's not invertible. The operator would not be invertible, and specifically, there's a simpler. How do we know that operator is not invertible? It is determined by what is it? Determinant. It is determined by the determinant, yes. So, so whether or not such a solution exists is determined by the determinant. So then it is in fact if and only if. If and only if determinant of the matrix, the new matrix, however, it's not the same matrix. So when the determinant of what matrix? This matrix, not the original matrix, this matrix, when the determinant is equal to 0, then there will be a non-zero solution. Okay? So in other words, determinant of the following matrix, 1 minus lambda, 2, 3, 4 minus lambda, equal to 0. That's what guarantees the existence of such a solution. So which means that we need just to solve it. It is an equation with respect to lambda and nothing else. You just solve it and you'll find the answer. So that's the idea. I wanna pursue this next. You just compute the determinant, you're pretty much done. So just to suggest what the next step would be, and it will be 1 minus lambda. Remember how determinants are computed. Minus 6 is equal to 0. Solve for lambda. So lambda then is found in a much easier way than the eigenvalues are found through solving nothing but a quadratic equation. So instead of solving a system of linear equations that we did when we used the definition of the eigenvalues, and you have to deal with x and y at all times, and there are some cases, this case, that case, that certainly long term is not going to work in higher dimensions, but this idea will, and because all you have to do is just to solve an equation. It's not linear, but it is a single equation, and there are no x and y's to worry about. So a quadratic equation, you solve it, you got your lambda, probably you're going to have 2, right? It is a quadratic equation. So before doing that, examples like that, let me go with the definition, or not with the definition, but repeat this analysis that we just had. Which is, dimension n, so A is from Rn to Rn. Okay, then the matrix equation Ax is equal to lambda x is equivalent to another, which we just did. How? I just pull everything from the left-hand side, from the right to the left, the same way. So Ax minus lambda x equal to 0. Then I factor out x. If I just know what this means, can I factor out x here? Unfortunately, not directly, because lambda is a number while A is a matrix. So I have to convert multiplication by lambda into matrix language, which we just did a few minutes ago. How do I do it? Ax minus lambda in x equal to 0. Right? So a bit tricky, but a little bit of a trick, but now I can factor it. I'll have A minus lambda in x equal to 0. Okay, now this is a system of linear equations, matrix equations, with 0 on the right. X is where it belongs. The matrix then we have to deal with is what's inside the parentheses. Okay? So it has a non-zero solution if and only if the determinant of the matrix is equal to 0. Okay, so and then we solve it. So we have to know the determinants there. Then, which is a challenge considering we only did 2 and 3 dimensions, 2 and 3. So what happens in dimension n would still have to be worked out. But it is an equation to be solved, and I'm not going to solve that equation because that equation at the top for the reason that, well, first of all, let me make sure that we know what the matrix looks like in n-dimensional case. It is, so you start with the matrix A11, A12, A13, okay, A1n, A21, A22, A23, A2n, A31, A32, A33, A3n, okay? And then, so that's my original matrix A. Now, if I subtract lambda in, what happens is only the diagonal elements will be affected, right? So I will just subtract lambda. So this part over here will produce this on the diagonal. And that's it. So that's my my matrix over here. That certainly will help us eventually. But at this point, let me just do one example. I don't want to do the same. Oh, well, let's do the same example to confirm that it works out. So my matrix A is 2, 3. Okay, so I form that matrix over there, the determinant of 2, 0, 0, 3. Well, I pretend that I don't know what lambda is. Identity matrix, right? Like this. I simplify. I have the determinant of 2 minus lambda, 0, 0, 3 minus lambda, right? And the determinant is easy. 2 minus lambda, 3 minus lambda. I set it equal to 0, solve, and I immediately discover that lambda is equal to 2 and lambda is equal to 3. Okay, so instead of trying to find eigenvectors and eigenvalues at the same time in one swoop, instead we just find lambdas this way, and then we deal with eigenvalues and eigenspaces, eigenvectors and eigenspaces separately when necessary. So I have a couple of minutes. Let me show you the what this is. It computes the eigenvalues. You see eigenvalues, right? Right there, written eigenvalues. It also finds eigenvectors, 1, 0, 0, 1, or rather negative 1, 0 for some reason. But the eigenvalues are here. I could change here. Say I put instead of 3, I could put. Well, let's confirm. If I put 5 here, so eigenvalues now are 2 and 5. If I put anything here, say 1, what's going to happen is eigenvalues don't change. So I changed one non-diagonal element, and the result was no change in the eigenvalues. But what does change is the eigenvectors. Okay. So all right. So we'll just continue next time with this.